In section 4.6, we're going to be looking at the graphs of the other four trig functions. So that's secant and cosecant, tangent and cotangent. I want to start with secant and cosecant because those are very related to the graphs of sine and cosine that we just studied. So in this video, let's take a look at y equals secant of x. And I want to just remember the definition is that that's the reciprocal of cosine of x. Okay. So what I'm going to do in graphing this is I'm going to start by actually graphing cosine. But I'm going to draw that as a dotted curve because I'm reserving the solid curve for points that are on the graph of secant, not the graph of cosine. So just like when you have an asymptote, you draw it as a dotted line rather than a solid line, we're going to do the same thing with cosine, which I'm thinking of as sort of a helper curve. So I'm going to mark off my quadrantal angles. We've got 0, pi over 2, pi, 3 pi over 2, 2 pi. Those would be the quadrantal angles for one period. High value of 1, low value of -1. And the pattern for cosine is that it starts out at a high value. So we go high, middle, low, middle, high. And now I'll connect those points with a dotted curve. Okay. Now, half the time when I try to draw a dotted curve, I forget and I draw it as a solid curve and then I erase part of it. If that happens to you and it's hard to tell that you erased it to make it a dotted line, totally fine to just write me a note in words. The cosine graph is dotted. Okay? Do your best to erase it and actually make it dotted, but sometimes it's hard to see that. Okay, now this gives me some information. I'm going to actually start with the places where cosine is 0. Because I know those places, secant is going to be undefined because I can't have 0 in the denominator. So there won't be a point on the graph at these places, but I want to see what happens close to these places. And I can see we've got pi over 2, 3 pi over 2. If I look at the unit circle, I can basically see any angle whose terminal ray passes through one of these points, 0, 1 or 0, -1. Because that makes the capital X value 0. Cosine is the capital X value, so secant is its reciprocal. Okay. Notice any angle whose terminal ray passes through one of these points corresponds to an odd multiple of pi over 2. I know that quadrantal angles are multiples of pi over 2, but this is 1 pi over 2, 3 pi over 2, 5 pi over 2, and I also get the negative odd ones. Negative pi over 2, negative 3 pi over 2. So basically any odd multiple of pi over 2, secant is going to be undefined. But what I want to know is what happens close to there. Because if I'm at an angle that's not exactly terminating on the positive y-axis, it's going to be close to here. So that means the capital X value is going to be close to 0. Sometimes positive, sometimes negative, but it's going to be a very, very small number. So close to these odd multiples of pi over 2, secant is the reciprocal of something small. But the reciprocal of something small is big. If you think about it, if I take 1/1000, I think of that as relatively small. The reciprocal of that would be 1,000. If I take 1/1,000,000th, the reciprocal of that would be 1,000,000. When I take the reciprocal of something small, I get something big. How do we indicate graphically when our y values are getting really, really big? We're going to have a vertical asymptote. So wherever cosine is 0, secant is going to have a vertical asymptote. Okay. Now, right now, I'm just working with this one period of cosine from 0 to pi over 2, from 0 to 2 pi. I'm going to adjust later, but right now I can see I've got asymptotes here, and I think I'm going to actually extend a little bit to my next place where cosine would be 0, which would be negative pi over 2, so I'd have an asymptote there. And if I extend it over here, we'd have 5 pi over 2, and we'd have an asymptote there. As a general rule, if you're drawing a trig function that has asymptotes, it's best to start and end at an asymptote. Okay. Notice these asymptotes In between each asymptote, I have what I'm going to refer to as a bump on the cosine graph. But here, the bump is above the x-axis, so my y values are positive. Between these two asymptotes, the bump is below the x-axis, so my y values are negative. That's super important, because when I take the reciprocal of something positive, I get something positive. And when I take the reciprocal of something negative, I get something negative. So the plus or minus sign of secant matches the plus or minus sign of cosine. Okay. So I know secant's going to be positive in between these asymptotes, negative in between these, positive in between these. And if I look at the pattern, for this bump of cosine, the y values start small, they go up till they hit their biggest value, and then they get smaller again. For the negative bump, if I look at the absolute value of things, they're negative values, but if I look at the absolute value, this is a small absolute value. We go down to the biggest absolute value, 1 below the x-axis, and then we come back to a small absolute value. So the absolute values are going small to the biggest value back to small. When I take the reciprocal, that's going to be reversed. We're going to go big to our lowest value, or our lowest absolute value, smallest absolute value, back to big. Okay. So I can pretty much see that instead of having a bump like this, I'm going to have something like so when I take the reciprocal. Starting big, coming to a low point, getting bigger. And that low point will occur at the same place that cosine is at its biggest value. So what's the reciprocal of 1? Well, the reciprocal of 1 is 1. So this point is going to be on the graph of both cosine and secant. And I'm going to have something like this for my graph of secant. Here, I'm going to have that, but upside down. If the absolute value starts big, a big negative number is way down low, we're going to come up to a high point, which would be the reciprocal of -1. And the reciprocal of -1 is -1. So the graph of secant and cosine agree at that one point. The low point on the graph of cosine becomes the high point on the graph of secant. So I have what looks like a sequence of alternating parabolas. Now these aren't parabolas, because parabolas would be infinitely wide. These are squashed in between these asymptotes, but they sort of look like that. It's the same sort of U shape, and they're just alternating like so. Okay. And I would have another one over here, and you can see the pattern's going to just go one that opens up, one that opens down, one that opens up, one that opens down, etc., etc., etc. Okay. Kind of cool. Okay. I like to refer to this as flipping the bumps. So you draw your graph of cosine. Wherever cosine is 0, you draw in your asymptotes, and then you flip the bumps. You've got a bump in between each consecutive pair of asymptotes, and you just flip it. Okay? And that gives you your graph of secant. Okay. So there's secant. Now what I've graphed here is actually 1.5 periods. The period is going to be 2 pi, because a period will consist of one flipped bump that opens up and one that opens down. Okay. So the period is 2 pi. We're not going to talk about amplitude. Amplitude doesn't make sense. Amplitude was measuring how high something was. This goes infinitely high and infinitely far down. Okay, so amplitude applied to sine and cosine. It's not going to apply to the other trig functions. But all trig functions are going to be periodic because they all repeat a pattern as we go through our angles. And so the period for secant is 2 pi. Okay. I can also talk about the domain and the range. If I look at the domain, I can see it's defined everywhere except at the asymptotes. So I'm basically getting an infinite union of intervals from -pi/2 to pi/2, from pi/2 to 3pi/2, from 3pi/2 to 5pi/2. Now if I just had 1 or 2 intervals, interval notation would be convenient. When I have infinitely many, I'm probably going to want to switch to set builder notation. So I'm going to say my domain is the set of all points of all values x such that, we read that vertical bar as such that, okay, and it's going to be everything except the locations of the asymptotes. So it's going to be that x is not, now I said the asymptotes occurred at odd multiples of pi over 2. So here's one way that I can do that. I'm going to say it's going to be an odd multiple of pi over 2. Now I'm going to use an integer n to describe things. So I'm going to say that the integer that I'm using is z. But integers can be even or odd. But if I take any integer and double it, I'm going to have an even integer, because that's the definition of an even integer. It's a multiple of 2. If I take an even integer and I add 1 to it, I've just made it odd. So I can say 2n plus 1 is a nice way of describing an odd integer. So this is saying everything except an odd integer times pi over 2. That's going to be my domain. Now, if you prefer, when we looked at the unit circle, we saw we were ruling out any angle whose terminal ray passed through a point like so. The other way I could write this, and this is equivalent, is it's the set of all x such that x is not pi over 2 plus n times pi, where n is an integer. Because pi over 2 would put me here. If I add a multiple of pi to it, an odd multiple of pi would bring me down to this point, and an even multiple of pi would bring me back to a point that's coterminal with that angle. Okay, so either of these describes all of the points that we can't plug in to secant. So that's going to give us our domain. Let's go ahead and state the range, and then I think we've got it covered. Now for the range, I am going to use interval notation, but it's going to be 2 separate intervals, because notice there's this no man's land in here. Okay. The graph of secant gave me y values that were 1 and bigger, or -1 and smaller. So I can say negative infinity to -1, including -1, union 1 to infinity, including +1. Okay, excellent. Now, if I ask you to graph this, like I said, I've here graphed 1.5 periods of secant. Generally, if I'm asking you to graph, I will specify graph exactly this many periods. So I might say graph exactly 1 period, or I might say graph exactly 2. If I said graph exactly 1, what I'd want to do is just erase part of it. This is exactly 1 period now. Okay. And I could have erased this one or this one. That gives me 1 positive flipped bump, 1 negative flipped bump. Okay. I will always also ask that you start and end with an asymptote. Notice, if I had just graphed from 0 to 2 pi, I would have half of a u, a full upside down u, and then half of a u. That doesn't really capture the pattern as well. So it's always best if you start and end with an asymptote, and I will always ask for that when I'm asking you to graph one of the trig functions that has asymptotes. So for secant, starting at 0 isn't a good choice, but you notice that. Once you draw your cosine and you realize, oh, cosine isn't 0 here, you just say that's not a good starting point. I'm either going to start here and go to here, or I'm going to start here and just go from -pi/2 to 3pi/2. Okay, either of those would be an acceptable choice. Usually I go from -pi/2 to 3pi/2 if I'm graphing just 1 period.